So, welcome to everybody. Here we are. This is Alberto Casagrande. I'm your teacher of Algorithmic Design, and this is our home, let's say, for the course of Algorithmic Design of this semester. I hope you can hear me. I'm not sure about it because this is the first time I'm using this kind of technology, and however we will try to improve let's say the result by the end of this course. So first of all, I want to welcome, and I want to spend very few words about the situation. Let me first of all show you my face just to try to find a normal situation, let's say. Well, as you imagine, we were not prepared for this kind of issues, and so right now we are trying to organize all the teaching by using this kind of tools. The university itself is testing an integrated environment called Microsoft Teams, which at the moment is not ready yet, let's say, for the usage, but eventually all the courses will move there. And in the meanwhile, all the teachers feel their duty to start the courses. And so many colleagues of mine already started the courses the last week by using Twitch. I opted for YouTube because from my point of view it's easier to handle all the recordings, and I know that many of you already had a Google account. So since a Google account is required to interact with me by using the chat, the YouTube chat, I thought that this is the best way to provide you this course. Of course, having a Google account is not mandatory. I'm not going to force you to have it, and you can still interact with me by using emails. Well, the chat is almost on live. I say almost because there is a small delay due to the streaming delay, so probably, 30 seconds or something similar. It depends on the bandwidth I have right now. And while the email, of course, takes more time to be read. And then I will try to answer all the questions sent by email on the next lesson, at the beginning of the next lesson, but please don't be shy. So this is it. This is more or less what I'm going to do. So I'm going to provide you the course by using this tool, which is not perfect. And first of all, because the course itself is not perfect, I'm not perfect at all, and however, the course was not meant to be given in this way. So it was based on interaction between you and me, and the non-verbal communication was meant to be a fundamental part of the course itself. So looking at your faces, I can understand whether I can push forward the topic, or hold back and make more examples. Unfortunately, this is not possible by using this tool, which is great but still not perfect, as I said before. So we will try to tune it during the next week. I think this is more or less all I want to tell you at the beginning of the course. As I said before, you have a chat, you can send me a mail, and so on and so forth. So feel free to make suggestion, I don't know, evaluate the situation of the course right now, and I mean every helps in trying to obtain a better result for this course will be helpful, and of course I appreciate it very much. So let's move to the course itself, and just for the sake of testing it, can you send me some messages in the live chat? If you can, I would see them during my presentation. So let me move to the slides. Oh, by the way, the slides will be available on Moodle. All the slides will be and the material. So we are going to perform coding. We are going to do some exercises and so on and so forth. All the materials would be available on Moodles, and I will provide you for free, let's say, of course. Okay, and also the course itself, so the video will be available on YouTube. So I'm recording the course, and you can see all the lessons in the future, of course. Okay, I can see your messages, so great. So let's move to the course, to the course itself. So as I already said, I'm Alberto Casagrande. I'm your teacher, and okay, here's some information about me. Well, the office is not really useful right now, but hopefully by the end of the semester you will come to my office. So here you have, and this is it. So what's this course is about? This course is about efficiency. During the first semester, you focus your attention on how to write programs, and right now we are moving our focus on writing efficient programs. Okay, so where efficient is not clear, of course, right now, because efficiency is a very untouchable words. So during the course we will see some abstraction for the notion of program. We will define a measure of efficiency and complexity. We will see some technique to compute this measure, and we will go through some widespread problems and most effective solution for them. Okay, so this is more or less my program for the course, and now you may wonder why learning algorithmic design is useful. Well, of course, the point is that there are infinite programs to solve the very same problems, very same problem. So if you fix the problem, you have an infinity number of programs that can solve that problem. So for instance, let's imagine we want to compute a function. There are infinity ways to compute that function. And the point is that we want to, of course, to achieve the best efficiency. So we want to get the program that is able to compute that function in the shortest amount of time, for instance, or by using the short amount of memory. And a possible solution to achieve this goal is, of course, implementing all the possible programs. But since they are infinity, and there are infinity of them, this is not possible at all. So another way to solve this problem is to use algorithms. So by trying to model the programs of itself, an high level of the programs of itself, we are able to discriminate the best solution. We may be able to discriminate the best solution and to decide whether a proposed solution is not feasible at all. Okay, so for instance, let's imagine a situation in which we want to sort a set of numbers. So we have 1, 3, 4, 5, 6, 7 up to 100, and to sort them so that the shortest number is the beginning of our list and the largest number are the end of our list, we may try to compute all the possible permutation of this number and then test whether the sorting property is preserved by the permutation we have computed. Well, of course, this is a correct program. It works from an ideal point of view. However, from the algorithmic point of view, it's not really smart because it takes a time which is exponential in the number of the numbers. So depending on the architecture in which you're trying to implement this kind of solution, you may end up in a solution which is not achievable in 4 billion years. Okay, so of course that's why it's really important to try to model the program before implementing them, and that's why algorithmic design is important. Another reason to study algorithmic design is to try to identify the best solution for a specific program. Okay, so of course among a set of solutions, so the best solution would be the one which takes the least amount of time or wasted the least amount of memory, and this can be done without implementing the programs themselves. Okay, just by looking at the algorithmic design of the possible program we want to implement. Finally, studying algorithmic design of programs let us to unravel the real nature of a problem. So to achieve the best solution, the overall best solution, we really need to understand where the point is. And we will see an example of this last point very soon during the course. Okay, let me move on. So how we will learn algorithmic design? Well, of course, we will have these lessons. We will try to do some exercises, and you will be requested to solve some homework. Okay, and by homework I mean implementation of what we are going to see during the lessons. Sorry. So, however, we will see later later on what I mean by implementation. Okay. So the idea is that the most demanding task of the overall learning process will be the homework, because you will be implemented. You will be requested to implement some of the course topic in C or C++, and you will be avoided to use external libraries, STL or Boost or everything else which help you in writing code. And the motivation to avoid all these libraries is that I want you to touch with your hand the difference between designing an algorithm and writing the corresponding program. Okay, so designing an algorithm, handling algorithm is really much easier than writing programs, and there is a small gap in understanding the problem and writing the correct algorithm with respect to writing the program, which should be filled by this homework, basically. So studying the topic we will see during the lesson and completing your homework should take a couple of hours per lesson at most, of course, if you follow the lesson. And if this is not the case, please let me know. Okay, we will try to decrease the amount of homework, or we will see how to manage the situation, because of course this is a really unnatural way of having lessons, and so I need your help to understanding what's going on at home. Okay, and so when are we going to have these lessons? Well, my intention is to maintain the standard lecture plan. So we will have the lesson on Monday, Tuesday, and Thursday at 9 a.m. And this is it. Okay. As I said before, all the lessons will be recorded, so if you want to see them in different hour, is not really a problem for me, but of course you will not be able to interact by using the chat. So what kind of course is this? Well, you come from really different backgrounds. Some of you come from mathematics, some of you come from physics, biological studies, engineering, economics, computer science, and so on and so forth. So many of you need an introduction to algorithms, okay? And so even though the course was originally thought to be an advanced course, we need to introduce all this topic. So the course consists in two parts which are interlinked in some sense. In the first part, we are going to see all the preliminaries. So we will talk about asymptotic complexity, we will see the sorting algorithms to solve the sorting problem I mentioned before, basically. We will see binary search tree, redback tree, and so on and so forth. We will see some algorithms, some graphs, short-term path problems, and so on and so forth. Don't worry if you don't understand right now what I'm talking about, because we are going to start from the very beginning and present all these problems completely. For all of you that already know what I'm talking about, we will have also less usual topics. So, for instance, we will talk about a really nice problem about the matrix multiplication. You all know probably the matrix multiplication definition, so row by column matrix multiplication, and we will present the Strassen algorithm to multiply two matrices, which is surprisingly fast. Okay, and we will try to unravel why the problem can be solved in such a small amount of time. And we will see transitive closure of graphs, we will see routing problems, so we'll try to investigate how, let's say, just to make an example, how Google Maps works, and so on and so forth. We will see some algorithms on string matching problems, and hopefully, but this really depends on how the course will go on, we will see suffix tree and suffix array, which are two data structure to solve a pattern matching problem in linear time, basically, and we will see what I'm going to talk, what I'm talking about by the end of the course, hopefully. I really don't know. So, as I said, this course is meant to be in some sense introductory, in some sense more or less advanced. Okay, not really advanced, but we will see unusual topics as you can see on the slide. Okay. So, should you attend the course? This is a really funny question to be asked during an online course, of course, and that's because the course wasn't meant to be given online. But you can interpret it as, should I follow the course during the streaming? Well, the attendance is not mandatory, of course. Okay. And you can follow it simply by looking at the recording or by studying on the book. However, following the recording or following the streaming give you a high-level view of the topic without spending much time reading the book. Okay. So you may have a full overview of the very basic notions without spending many times in understanding it on the book. And this is, an advantage for who is starting. Of course, if you are not a novice, you don't need preliminaries. However, I think that it may be useful to recap everything before the unusual topics. So my suggestion for all of you is to follow it. And by the way, this gives me the chance to understand whether you can understand or not. Okay, so if you follow it by online, by following the stream, I can understand whether you have questions about a specific topic or not. So the textbook I'm following is the Introduction to Algorithm by Corman, Leverson, Rivest, and Stein, and this is a sort of Bible of algorithms. So if you are interested in the topic, I really suggest to buy it. It's a really great book, plenty of interesting algorithms, more algorithms than the algorithms we are going to see, and probably we are going to use just 1/3 of the book, and that's all. However, as I said, if you are interested in the topic, this is really a must book for you. Okay. Great. So the course material, as I said during the introduction, I'm going to give you all the material, including the slides, the exercise we are going to do during the classes, and the code we are going to encode during the classes. So you can find all these materials on Moodle, and the link to my Moodle is that one. Let me go back just to the book. Someone is asking whether there is any book for the same topic, and is asking whether you can download it. Well, I really don't know. I know there is a PDF version of that book, but I don't know whether it is official. Let's say, I suppose you can buy the PDF version of that book. Okay, I don't know whether there exists an ebook version, which is not exactly the same. Okay, this is it. Sorry again, but talking for 1 hour and a half alone is not that easy. Okay, so going back to Moodle, you can right now try to enter in Moodle and see whether you can find the slides I'm using right now. Okay, just try it. If you are not sign in, let me know. I try to fix all the stuff, but just try during my presentation, okay? And let me know on the chat. Oh, by the way, as you see, the password, you need a password to sign in on Moodle, and the password is Dijkstra. It's this strange name we will learn to pronounce during the course, $. So, now, the most interesting part of this introduction is, of course, the exam part. So, in many years, this is the part in which every student wake up from its sleep, and so please pay attention to it. So what about the exam? The exam will consist on the homeworks, which you will be requested to do during the course, and a final written exam. This was my intention just before the emergency, but of course, since we are not going, we don't know when this emergency will end. This is my program, and this program can be changed depending on the situation. Okay, so I'm not sure about this exam right now because of the emergency, and it will really depends on the evolution of the band. Hopefully, I don't know what you think about the final written exam, but hopefully we will have it. Okay, and you shouldn't really worry about it, because we are going to have many exercises during the course. So if you follow the course or study at home, probably it would be that difficult to pass the final exam. Okay, if you have any question about the exam, please feel free to send me something on the chat, and I'll answer as soon as I receive the message. Now, okay, as you see, I haven't changed the slides, so at this point you are able, you can ask any question you want about what I said until now, and in the meanwhile, while I'm changing the slides, so moving to the next topic. So let me go here, and here, and this is here. Okay, here we are. Are you still there? I think so. I hope so, at least. Let me see. Okay, this is it, and this is it. So the first topic, the very first topic I want to talk about during this lesson is the basic notion we need to know to study algorithmic design. And let me see what's going on here. Okay. And so we need to introduce algorithms and computational models. So the very first definition we need to give is the definition of algorithm. So what's an algorithm? Okay, an algorithm is a sequence of well-defined steps that it's able to transform a set of inputs in a set of outputs in a finite amount of time. So here the definition is quite vague, because we are not saying what we mean by steps, what we mean by input, what we mean by output, but we want to stress the fact that this process need to being able to transform something in something else in a finite amount of time. Okay, we don't know how much time, but this time should be finite. Okay, now of course we also need what we call computational model. So again, I'm going to give you a quite vague definition, but still probably you can figure out what I'm talking about. This definition is the definition of computational model, which is a mathematical tool, okay, so a machinery, let's say, a mathematical machinery to perform computations. So sums, subtraction, is able to increment by one values, is able to test whether two values are, it should be able, let's say, to test whether two values are the same values or not, and so on and so forward. So the computational model itself depends, of course, on the operations that you are able to perform on it. Okay, the more complex, the more operation you are able to perform, probably the more complex is the computation you can achieve. Okay, this is not given by granted, but this is what you can imagine. Okay, now a function. So ideally we want to compute function. Okay, so any programs you have in mind basically transform something in something else. So is evaluating a function. So a function described by an algorithm is called calculable. So a calculable function is a function which is describable by an algorithm. A function which can be turned into a program in a specific computational model is called computable. Okay, so these are two different notions. Calculable means I can describe the function by using an algorithm. You can imagine an algorithm just like a receipt for a cake. First take X, then and so on and so forward. While a function which can be implemented, so encoded into a program for a specific computational model is called computable. Okay. Now, a very basic question you may wonder is whether all the function computable, whether all the functions are computable in any specific model. So is there a function which is not computable in a specific model? So if this is the case, so if there is a function which cannot be implemented in a particular computational model, then you may wonder whether there are calculable functions or functions describable by algorithm which are not computable, or the vice versa. So it's possible to have a computable function which is not calculable at all. So a function which can be described in a program but not by an algorithm. So the point is, given the intuition of what is an algorithm and given intuition what is a program, are we sure that whenever we have an algorithm we are able to encode that algorithm into a program? Okay, this is the point. And just to try to answer the first question, so just to try to understand whether all the functions are computable in a specific model, let's try to investigate whether a specific function is computable, and that specific function would be okay, this is what I've just said, would be the function to compute whether a program is going to end or not on a specific input. So let H be a function, okay, that the function that establishes whether a program P eventually ends its execution on a specific input I, or whether it runs forever on that specific input. And this is the definition of that function. So H evaluate P and I and return 0 if Pi never ends, or 1 otherwise. Okay? So here, notice that I'm not telling you anything about I, and for instance, I can be a program. Okay? So let's imagine a situation in which P is an antivirus. Okay, antivirus in this period probably is not the best example, but let's take this example. So if P is an antivirus which tests whether a specific program contains a virus, I is a program, okay, and P should evaluate whether I contains any virus, let's say, okay. So I can be a number, can be a program, can be anything you can imagine. Now, the question is, can I implement H? So the function which establishes whether a program, any program, let's say P, ends on a specific input I, can be implemented, so it is computable. So let's see. So for any computable function FAB, we can define the function GFI. So let's assume we have all the possible function taking two values as input, and these functions should be computable. So we take all the possible computable function taking two values as input. From that set of function, we can build a new set of function in which basically we do the following things. So GFI will be equal to 0 if the function f on I is equal to 0. Otherwise, the program should run forever. Okay? Now, it's quite easy to see that if f is computable, and this is the case because we are building this GF only on computable function, then so it is also GF. Why? Because just figure out a situation in which you are encoding your computational model is, I don't know, Python, for instance, okay, and you can write the program corresponding to GF simply by first of all trying to evaluate FII and getting the result. Then you will have something like a conditional statement testing whether the result of FII is 0. If this is the case, you return 0. Otherwise, you basically keep looping on a while statement whose condition is true. Okay, and the program never ends in this case. So if f is computable, also is so it is GF. Okay. So remember, this GF is the function. This GF is the implementation. So the program implemented the function GF, small GF. Okay. Now the question is, can our halting function, so the function which decides whether a program eventually ends on a specific input or not, can H be one of our computable function f? Well, let's assume that this is the case, okay? And let's try to evaluate the function f gf gf equal to 0. Okay, so if this holds, this means that by definition of gf, gf applied on the program gf is equal to 0 because of this definition. Okay, and since this holds, this means that gf ends its evaluation. This means that gf ends its evaluation. So by calling the function h on gf, we should end up with 1, because gf ends its evaluation on gf. Okay? So if f gf is equal to 0, then h gf should be equal to 1. What if f gf is different from 0? Well, if this is the case, then gf applied on the program implementing it should never ends. Okay, so should loops forever, let's say. If this is the case, okay, then h applying to gf should be equal to 0. Okay, why? Because we are basically evaluating gf by giving as input gf, and this loops forever. So the halting evaluation of gf on its input gf should be equal to 0. So as you can see here, in any case, in both cases, so if f gf is equal to 0, and also if f gf is different from 0, then h behaves in different way. Okay, so h should be different from all the possible computable function, and so h is not computable. Okay, this is a little bit tricky, but if you look at the equation, you can understand really that h, so the function evaluating whether a program can end, well, a program eventually end, cannot be computed in any possible computational model. Okay, which is in some sense surprising. So now the problem is, how can we map algorithms into program? Are we sure that having an algorithm in mind, that algorithm can be implemented into programs? Well, we can map algorithm into programs by using the Church-Turing Thesis. This is a thesis never proved by anyone, but this is I mean, it's still old until now, and we are talking about something which were presented I mean, more than 80 years ago. And the thesis says that every effectively calculable function is a computable function. Okay, so if your algorithm is built up by describing steps which are nice enough, let's say, so not too complex, then that algorithm can be implemented. Okay, so this also means that all the computational models reasonable, so if you don't introduce too many if you introduce enough function to be computed, so the sums, the subtraction, multiplication, and so on and so forward, the ability to test whether two values are the same or not, but you are not too nasty and you don't introduce something which is not computable, let's say, in your basic steps in your algorithm, then that computational model is equivalent. Okay, and it also means that we can avoid hard-to-be-programmed models. So we can describe algorithm by using Turing machine, but of course this would be a mess. So the idea is to use high-level models, computational model to describe, to map our algorithm, and to avoid hard to be understood, let's say, details. So our computational model, in this case, we are able to provide a computational model which is easy to be understood and quite easy to be programmed, and so we choose I choose to work with random access machine, which is a computational model providing variable to store data. We don't have types, arrays. We are able to work with integers and floating point constants. We are able to perform algebraic operations, so sum, subtraction, division, multiplication, floor, ceiling, and so on and so forth. We are able to assign values to variables. We have also pointers, but we don't have pointers arithmetic. If you come from C or C++, you know what I'm talking about. And we have conditional and loop statements, so if then else, and so on and so forward, while, for loop, and so on and so forward. We are able to define procedure. We are able to define recursion, and so on and so forward. Moreover, we have also reasonable functions, such as evaluating the length of an array and this kind of stuff. Quite simple functions. Okay, so all the algorithms we are going to see will be defined as program in round. And just to have an example of it, let me show you a small naive algorithm. Okay, so this algorithm takes as input an array of numbers a1, an, and as output it should return the maximum among all the numbers taken in input. Okay, so as you can see here, we are defining a function more or less like we may do in writing a Python program. Here we are saying that we want to assign a value to the variable max value, and this is done by indexing by 1 the array A. As you see here, the first element in the array is always index 1, and the last element in the array will have as index the length of the array. So it's a little bit different with respect to C or Python, in which the indexing starts from 0 and then ends in the length of the array -1. Okay, this little difference is useful in writing algorithms because avoid you to confuse things, but I mean it's not really mandatory. Okay, it's just to simplify in some sense the description algorithm itself, because if you take the first element of the array, you have index 1 and so on and so forth. So as you can see here, we are able to go through all the elements of the array by ranging from 2 up to the length of the array itself, which is described in this way. So this notion means basically the length of the array A, and these two dots means I want to go from 2 to length of the array. And here we have a conditional statement, which basically tell us that whenever we find a value in the array which is greater than the maximum value, already established maximum value, we want to assign the variable maximum value with that value, and at the end we will return max value. Okay, so quite simple, not really nothing to be understood at this point. This is just an example of an algorithm and how we will deal with it. Now, it's important to understand that RAM is not, so RAM models and RAM algorithms are not real hardware and programs, okay? Because RAM is meant to model real hardware, but lacks some really important things. First of all, RAM does not have hardware limitation. So, for instance, in a variable you can store any possible values, any possible natural values, any possible floating point number, which is of course not the case for the real hardware, which has some limitation due to the limitation of the hardware itself. Okay. Another difference is, for instance, the memory hierarchy. So in real hardware we have first level cache, second level cache, we have the RAM, we have many different memories which are not present in RAM. So in RAM we have memory, and that's all. And doesn't matter where a certain kind of data is stored, you can access it as we saw exactly in the same amount of time. Moreover, in RAM we don't have instruction execution time. Okay, so we can imagine that every instruction takes exactly the same time and is instantaneous. Okay, well, this is not the case for real hardware, of course, because executing a sum between two natural number takes a different time with respect to executing a division between floating point number and so on and so forth. Okay, so let's move to time complexity. So right now we know what's an algorithm, what is a computational model. We saw how to write our algorithm. We saw that there exist functions which are not implementable, but if we limitate ourselves to dealing with functions which are describable by algorithms, that functions can be implemented in any computational model by exploiting, let's say, the Turing Church-Turing Thesis. Okay. Now, the goal of our course is to develop an algorithmic design technique which is able to tell us whether an algorithm is more efficient with respect to another. So right now we need to define what we mean by complexity of an algorithm. Okay. So how can we measure the efficiency of an algorithm? Well, the very first answer we can provide to this question is execution time. What about using execution time? Well, here we have a problem. First of all, we don't know for which input. So the execution time of a program really depends on the input. Sorting one element is quite different from sorting 1 billion elements. Okay. Moreover, algorithms are not programs. So if we assume one time unit per instruction, we get something which is not realistic, because the execution time of the programs depends on many factors. Depends on CPU instruction sets. So running a program on AMD CPU or Intel CPU is quite different. Depends on the CPU itself, depends on the memory, depends on the bus clock, depends on the language you implement the program. So writing a program in C or writing a program in Python by implementing exactly the same algorithm, it's quite different. Okay, of course you could achieve a much better result in terms of execution time writing the very same program in C. Okay, but even if you decide to write the program in C, the execution time depends also on the compiler you decide to use to compile your program. So writing a program in C and compiling it by using GCC or C-lang may turns out in a really different result. Okay, so as said, algorithms are not programs, so it's not possible, even by assuming we already have an input, it's not possible to evaluate estimate, let's say, the execution time of the program just by looking at the algorithm, because there are many other factors on which we don't have any control. So execution time is not the right way to evaluate the efficiency of an algorithm. Do you have any other idea about it? Are you still there? Okay, so let me see. Okay. So a possible solution to measure the efficiency of an algorithm is scalability. What I mean by scalability? Asymptotic analysis. Yeah. So what I mean by scalability? So the scalability is the effectiveness of a system in handling input growth. Okay, so how effective is an algorithm in handling 100, an input containing 100 number, an input containing 1,100 number, an input containing 1 billion number. Okay, so let me give you an example. Let's assume we have a situation like the one you can see on the slides. We have this table basically relate the input size of a particular algorithm and the execution time of the algorithm itself. Okay, by measuring the execution time, basically we are plotting one single dot inside this graph. Okay, so we are saying by taking that input size we end up in an execution time which is this one. Okay, but we as already said, we are not able to do it. What about measuring the scalability? So we want to estimate, in some sense, not the single plot, the single dot, but we want to evaluate, estimate the growth of this function. So we want to relate the input size of our algorithm with an estimation of the execution time. Not really the execution time, but something similar to the execution time. In this way, we are able to say, okay, I don't know what's the execution time for an input of size, I don't know, 2000, but I can in some sense estimating it by evaluating this function. Okay, so we are not focusing on the execution time itself, but we are focusing on the growth of the execution time with respect of the growth of the size, of the input size. Okay, now a small quiz. what do you think? Which growth is preferable between n squared and n? Okay, here in red we have a growth, we have the function n, and in blue we have the n squared function, and here we are saying that for size 2 we have this execution time, for input size 4 we have this execution time, and so on and so forward. And here you can see this is the n squared growth. So which of the two growths is preferable? Well, of course, as as I see on the chart, the red one is preferable, because we are basically saying that the execution time from a certain point on, from this point on, is smaller for this function. Okay? Now let's move on, and let's say, what about n squared and 2 times n? Okay, so n squared is still there. This is n squared, and I replace n by 2n. So which of the two is the preferable growth? Well, of course, again, from a certain point on, the red one is the preferable growth. Okay, but here we can see that there is at least one input size in which the red one is growth, for the red one growth has an execution time which is greater than the blue one. Okay, but still we don't care about it, because we are reasoning on the growth, so on the asymptotic evolution of these functions. Okay, so again, here if I should choose between n squared and 2n, of course I would go with 2n, even though there is one case in which n squared is preferable in execution time with respect to 2n. Okay, but we don't care about it, because from a certain point on, which is the case dealing with big data, for instance, from a certain point on, 2n is better than n squared. So what about n squared and 500n? Well, again, up to input size 500, the red line is preferable to the blue one, but from a certain point on, better from 500 on, the blue line is beyond the red one. So if I should choose between the two, for sure I would choose the red one. Okay, so these few examples tells us something really interesting. We are not interested in looking at the constant. Okay, we are looking at the asymptotic behavior of the function. So in some sense, n, 2n, and 500n are exactly the same function. Okay, behaves from the asymptotic point of view exactly in the same way. So we can from our algorithm, we can abstract the single instruction execution time. We are not interested in saying, okay, the sum takes 2 seconds, the multiplication takes 5 seconds, and so on and so forth, because we are abstracting from the constant by looking at the asymptotic analysis. Okay? This intuition that we saw on the example is also supported by a quite famous theorem, which I just going to mention. We are not going to prove it, because it's done Turing machine, which I mentioned before, but I haven't introduced, which is the linear time speed-up theorem, which basically says that we are able to build up a machine taking 1/2 of the time is taking the machine we are working on. For any machine, we are able to build up a machine taking half of the time of the previous one. Okay, so this is the intuition behind the fact that we are not going to use constant in our analysis, and we are only dealing with asymptotic behavior of the function. Okay, now the point is, how can we group together all the functions that behaves in the very same way? So we saw 3 examples before. We saw n, 2n, and 500n, and we saw that with respect to n squared, they behave more or less in the same way. So how can we group all together? How can we build up a equivalence class in which we can switch between n, 2n, and 500n without any problems? Okay. Well, we can do it by using the big O notation. What's the big O notation? The big O notation is what you can see on the slide, and is something I'm going to ask you during the exam. So please pay much attention on it, because it's quite important from my point of view. So by saying that, by writing big O f of n, I'm basically describing a function, a set, the set of all the functions for which holds something. Okay, so big O fn is a set of functions. Okay, so let's look at the example. I don't want we will go through the formula looking at the example, because I think it's much clearer. So let's say I want to test whether my function gn, which is the red one, belongs to big O fn, okay, which is the blue one. So gn belongs to big O of fn if and only if there exists a constant value c, in this case, for instance, 3, and there exists an input size, in this case 4, for which, for every value greater than the input size we identify by n0, my fn multiplied by the constant, in this case you can see the fn function multiplied by 3 is the dotted blue line, is greater than gn. So here we are saying that gn belongs to big O of fn if there is a constant which multiplied by fn and is equivalent to the dotted blue line, and input size n0 in this case is 4, for which for every input size greater than n0 the dotted blue line is greater than the red line. In this case gn belongs to big O of fn. Okay, as you can see from the very first slides, here can be a little bit confusing, because we are saying that by looking at the figure, seems that gn is greater than fn. But since we are able to find a c which multiplied by fn grows more than gn, we can say that gn belongs to big O of fn. Okay, so remember, there exists a constant value and there exists an input size for which for all the input size greater or equal to that input size, fm is smaller or equal to c multiplied by fn. Okay, so c fn top gn. So for this notation there are a lot of useful properties which allows us to work with big O fn just like it was a number, which is not the case. Big O of fn is a set, remember, okay? For instance, an important property is that big O of fn, fn belongs to big O of fn, which is straightforward, okay? But still is an important property. Another important property is that big O of fn is equal to big O of fn multiplied by c1 for any c1 plus k, for any k, okay? So, for instance, in the previous case we saw that n, 2n, and 500n behaves more or less in the same way, and as a matter of fact, big O of n is equal to big O of 2n and is equal to big O of 500n. Okay, so they belong exactly to the very same set. Okay. Another important property is the following one. So if for any natural number such that the first one is greater than the second, greater or equal to the second one, then big O of f and c1 plus k fn c2 is equal to fn c1. What does it mean? Well, if we have the function n square plus n, for instance, well, big O of f, big O of f square, big O of n square plus n is equal to big O of n square. Okay, so what is important in the function is the terms having the higher power. Okay, and we can totally avoid to remember the other part of the function itself. And of course there are many other properties that you can see. For instance, an important property is this one, which tell us, for instance, that n square, big O of n square includes big O of n. Okay, so by looking at this property we end up in concluding that n belongs to big O of n square, which is a little bit strange, but basically this big O means the function we are dealing with doesn't grow at most as big O of the function. Okay, now of course this big O notation gives us an upper bound for our functions, but we also need a lower bound for our function. Okay, so we need a lower bound saying the execution time is at least as, okay, and this property can be expressed by looking at the omega notation, big omega notation, which is this one. Okay, by looking at this function, which is symmetrical, but this notation, which is symmetrical to the one we saw before, we can provide a lower bound in the graph for our execution time. So we can say, for instance, that Gn belongs to big omega of Fn if and only if there exists a constant and there exists an input type, an input size, for which if I multiply Fn to my constant all the input size greater than the one I identified before. For all that input size, my dotted function is smaller or equal to Gn. If this is the case, then Gn belongs to omega, big omega of Fn. Okay? Quite clear. Now, what if I want to bound my growth, my function growth, from above and from below? Well, to do it, I can use the theta notation. Okay, you can see here the complete definition of theta notation, and there is a theorem saying that if Fn belongs to theta of Gn, then Fn belongs to omega of Gn intersected by big O of Gn. Okay, so in the intersection of big O of Gn and big omega of Gn, I have all the function that belongs to theta of Gn. Okay, great. So let's try to, in the last 50 minutes of this lesson, let's try to evaluate, compute the complexity of the function we saw before, of the algorithm we saw before, the one to compute the maximum among a set of numbers. So the line number 2, see here we have the, let's say, the algorithm. Of course, we don't have any costing evaluating the definition, let's say. We have a cost in evaluating a non-null cost in evaluating the assignment, of course, and this cost is theta of 1. Okay, we don't have any repetition, so the execution of this line does not depend on the size of the input. Okay. What about what is contained inside the for loop? Well, the execution time required by the time required to execute what is inside the for loop, of course, takes time theta of 1, because here we have a single evaluation of comparison, and then eventually possibly an assignment. But in any case, at most two instruction here. Okay, at most. And since we are not interested in the constant, it end up in saying we can end up in saying that the complexity of these two instructions is theta of 1, which by the case is theta of 2. Okay, not by the case, which is of course is theta of 2. Okay, here at most 2 instructions, so we end up in theta of 1. Now you may wonder how many times we are going to repeat these instructions. So the instruction from 2 to 5. Well, the number of times we are going to repeat this instruction depends on the length of the array. Okay, so the length of the array is n, because we wrote that a goes from 1 to n. So the number of times we are going to repeat these instructions is theta of n. It's linear, because we are repeating 1 time for each element in the array. Okay, so since the number of elements in the array is theta of n, the number of iteration of this piece of code is theta of n minus 1, which by the case is theta of n, is equivalent to theta of n because of the property we saw before. Okay,
So the overall cost, well, the cost of a returning instruction, of course, again, is theta of 1. So the overall cost of this algorithm is the sum of all these costs. So the sum of this operation, the sum of executing this piece of algorithm, so this instruction, and the sum of the cost of this instruction, which is 1, because this instruction takes the cost time theta of 1 plus theta of 1, which is the cost of this instruction, multiplied by n, which is the number of repetition of this instruction, plus the cost of returning function of this returning instruction, which is 1. Okay? Now, of course, if I evaluate this equation, I end up in n plus 2, but theta of n plus 2 is equivalent to theta of n because of the property we saw before. So the complexity, the overall complexity of this algorithm is theta of n. Okay? Is it clear? I think so. So if you have any question about this stuff, please let me know, and I'll try to answer your doubts. And okay. Okay, if this is more or less what I want to tell you right now. We are going to see some basic data structure, some useful notation, some basic data structure, some useful notation at the beginning of the next lesson, so tomorrow morning, and I'm waiting for your question. I'm waiting for your observation about the lesson, and please feel free to make any comment about it. And I don't know what to say actually. This is the all for today. The costs are different. Oh, sorry. I have a question, but the costs are different. Which one costs? Okay, so let me you are okay. Let me answer some of the question I just received. Some of your colleagues is asking, is it possible to have the slides in advance in order to be able to take notes on them? Well, the answer is yes, and they are available. Well, I don't know. Well, I'll try to make them available on Moodle the day of the lesson. Okay. I have already all the slides, but I don't want to spoil my lessons. That's why I haven't given you all of them right now. Okay. So don't worry. From the next lesson, I will try to. Well, I'll put them on Moodle before the lesson itself. So going back to the costs, someone is asking the costs are different. Which costs? And do you have time to go back to the Halting problem? I don't have clear why it's not computable. Sure, we have some time, so let me go back there. You're welcome. Okay, so let's look at the function meant to establish whether a program eventually ends its execution on a specific input. Okay, so if the program of that input I never ends, this function should return 0. Okay, otherwise 1. So if pi ends, this function should return 1. Is it clear? I think so. So going back here, and let's see here. Let's assume that a function f return 0 on gf. Okay. Now, by definition of gf, small gf, of the function gf, okay, this means that gf should return 0, because fii is equal to 0, so gf is equal to 0, so fi should return 0, should be equal to 0, and so gf should equal to 0. Okay, simply replace gf with I and you end up in the definition. Okay, now if this is the case, however, this means that f on this means that the program implementing gf on gf itself, this is the case, would return 0. Okay, so the program gf on the input gf ends eventually. This means that h on gf should return 1. Okay, because remember, h return 1 where the program gf on the input gf eventually ends. And this is the case. It ends and returns 0. Okay? Now, what about the case in which f on the program gf is different from 0? Well, if this is the case, then by this definition, gf should diverge. So should never end. Okay? Here. But if this is the case, then the halting function should return 0. Why? Because the program gf on the input gf never ends. Okay? I think this is clear. I think so. I don't know. Well, so we have just proved that for any total function, any computable function f, on this input on its input h behaves in a different way. So h differs from f on this input. The point is the result on f is not computable result on h. So right, cannot belong to f. Well, h cannot belong to the total computable function. So on gf, we have found an input on which h is different from f, which is by the case gf itself. Okay. Exactly. So your colleague is arguing that since h is always different from f for any f computable function, this means that h is not computable, and this is exactly the point. Okay. Okay. So this is all. I hope you enjoyed the lesson for today, and I hope to see you tomorrow, and we will recap some what we saw today, more or less, and we will see some usable data structure and let me answer one last question. Someone is saying number 2, number 5, number of line. Yeah. These are the number of the line. So line number 2 costs, which is this one. Line number 4 and 6, which are this one, and line number 9, which is this one. Okay. Sorry. I thought I was clear. However, this is it. So let's see you tomorrow. Okay. Thank you very much, and I really appreciate your help in trying to improve the course. Okay. Thank you. So see you.